Posso andare? Buongiorno a tutti, benvenuti. Io sono Luca Vincetti, sono il presidente di questa commissione di laurea di ingegneria elettronica. Vi darò una breve descrizione di come si svolgerà questa sessione di laurea, quindi non appena ci raggiungerà l'ultimo collega che compone la commissione, inizieremo con la discussione delle tesi di laurea magistrale. Ogni candidato avrà circa 12 minuti più alcuni minuti di domande. Dopodiché vi chiederemo gentilmente di uscire, in quanto la commissione si dovrà riunire per valutare il lavoro di tesi dei vari candidati. Terminata questa fase di valutazione vi richiameremo e procederemo alla proclamazione sia dei laureati magistrali che dei laureati triennali che nel frattempo ci avranno raggiunto. Per i laureati triennali facciamo solo la proclamazione, in quanto la discussione della prova finale è già avvenuta qualche giorno fa di fronte a una diversa commissione. E poi, come di tradizione, insomma, la sessione si concluderà con un brevissimo saluto da parte del Presidente della Commissione. Quindi la lingua veicolare, quindi la lingua con cui si tiene il corso di studio magistrale di Electronics Engineering è l'inglese, per cui tutta la fase di presentazione e discussione delle tesi avverrà in lingua inglese. Quindi adesso vi chiedo ancora di pazientare pochi secondi che attendiamo il completamento della commissione, poi partiremo con la presentazione del primo candidato. Okay, we can start with the first candidate. The title of the thesis is Analysis of Electronics of Racing Motorbike and Development of a CAN Control Unit for Control Purpose, Data Logging and Automatic Carburation Process.
Ok, prova. So, good morning everyone, I am Francesco Bergamini and today I'll speak about the analysis of the electronic of racing motorcycle and in particular to the CAN control unit that I have developed for control purpose, data logging and automatic carburation process. A motorcycle is a complex electronic system which is rich of devices that need to control the strategies in order to improve the safety of the rider and to optimize the performance on the track. The core of the motorcycle is the control unit, which receive as input all the sensor that highlight the state of the motorbike and also the input of the rider. Then elaborates this information in order to actuate, non so cosa sia successo, okay, in order to actuate the injectors or the other system, and all this information are sent to the CAN bus on the CAN bus of the motorbike, which is logged by external devices. In particular, the MKE7 control unit is the device used in all the Supersport 600 championship, and these are some of the strategies applied from the control unit. In particular, this graph represents the ride-by-wire profile. It is interesting to note that the first part of the graph is different from the higher part. This is because in the first part is represented the exit from the turn performed by the rider. Here, it is better for the safety and for a better progression out of the turns, a lower amount of torque in order to improve the capability of the rider to come out from the turns. Another important feature of the MKE control unit is the injection correction strategies. In particular, these strategies is correlated to the carburation of the motorbike. The lambda value, that is the value acquired by the oxygen sensor, is the parameter used to evaluate the correction coefficient that must be taken into the map. And in this way, it is possible to increase or decrease the amount of fuel injected in the combustion chamber. In this way, it is possible to maximize the performance of the combustion process of the motorbike. The problem is that the system does not follow a perfect mathematical constraints. Therefore, an automatic carburation process could be very useful. In fact, as can be seen here, the yellow line represents the actual value of the lambda sensor. It is possible to see that it follows a very fast behavior and a very fast dynamic, while the green line is the target of the lambda during the working of the motorcycle on the track. The desired aspect is that the goal is that the yellow line follows as much as possible the green line. And so it is possible to conclude that this is a bad carburation for the motorbike. After the carburation process that I have developed, this is the final result. Here, the dynamic of the actual lambda is smoother and follow the target that is a perfect line in this case, in both the condition during the straight of the track and also out of the turns here, where the TPS increase and also the regime of the engine increase. Therefore, it is possible to say that in this condition, the motorbike is well carbureted. Another important parameter to consider when the motorbike is on the track is the rider driving and the setup. From this, it's strange, but on this graph it is possible to see the first sector of the Mugello circuit. Here, the rider starts the braking, and it is possible to see how the shock completely extends, and this triggers a controlled slide of the rear wheel. This helps the rider to maximize the braking power and to settle up the motorbike in order to perform the better trajectory and start the progression of the throttle in the better way. From this graph, it is possible to modify the setting of the suspension and the geometry of the motorbike in order to improve the lap time. Based on this configuration, I have developed a CAN control unit for these four main functions. First of all, the CAN communication in order to understand what happened on the vehicle. Then, the elaboration of the acquired frame in order to modify some parameters. Then, a data logging in order to have some data for the post-processing process, and an automatic carburation process in order to improve what explained before. In particular, from an hardware point of view, the microcontroller the device is based on the STM32F103 microcontroller. That is a low-cost device and with a good availability. This device requires a CAN transceiver for the interface with the physical layer of the CAN bus, and also a buffer gate in order to settle up the communication with between the serial SPI of the microcontroller and the FAT protocol of the micro SD card. For the power supply, this device must be used on a motorbike, so a wide input voltage is required. Therefore, a complex buck converter and linear regulator are required in order to adjust the power supply. The firmware has been developed on the STM IDE, and in particular, I have developed two different firmware which follow the same process. The first one is developed for the university team Impulse Modern Racing, where the main problem is that the BMS send a multiplexed frames, a multiplexed data on the CAN bus, and therefore the other devices does not understand what the BMS says. So I have acquired the information, then processed the information, and replaced on the bus what happens inside the BMS. The other firmware is designed for the Panigale V2 of the Tokyo Motor Racing team. This is performed for what says before, for the carburation process. The carburation is developed using the MATLAB, and in particular follow this flowchart. The filtering process is based on the injection correction map, and so the TPS is related to the throttle position of the motorbike, and the RPM of the engine is related to the breakpoint imposed on the map of the control unit. The correction coefficient are calculated considering the average value of the acquired data for each point in order to find a trade-off between all the data acquired because are quite different from each other. Here are represented the results in two different types of tests. The first one is a track session. Here it is possible to see how the carburation process improves the carburation during the opening of the throttle, where the lambda result is smoother and nearer the reference value. At the bench test, during the bench test, in order to measure the maximum power of the motorbike, it is possible to see how the carburation process increase the engine power of 5 horsepower and also increase the available torque of 3.5 Newton meter. Okay. The device is for sure not perfect. This because it requires a lot of future upgrades. First of all, it is interesting to note that with an hardware upgrade that could be considered is the use of a dual-core microcontroller. This because the high frequency of CAN communication is required and may be performed of one of the core, and the other core is used for the slower data memory saving on the microSD, which require a slower process. Another important functionalities is the power management for the oxygen sensor. This because the previous control unit allowed the use of only one oxygen sensor, and this slows the carburation process for one cylinder per session. Therefore, if the control unit can manage all the required oxygen sensor, one for each cylinder, it is possible to speed up the carburation process. In conclusion, it is possible to say that the racing motorbikes are an extremely complex system, which requires transversal skills, but also a well-trained and prepared technician. But in this world, there is a wide space for the implementation of new devices, like the CAN control unit that I have developed. In particular, for my devices, it is possible to say that it performs it performs the skills for which it is developed. It speeds up and simplifies the post-processing work in the box, because the time between the session is always too low. And moreover, the carburation process increases a lot the vehicle performances on the graph and based on what the rider says. But for sure, the main problem is that only prepared people can use at the moment this device, because a lot of passages are required to put out the information and to calibrate the new injection map, and future upgrades are recommended. Thanks for your attention.
Thank you. Questions? Yes.
Right. Just on curiosity, you left us with two pieces of hardware.
Yeah.
One was exactly the one that you showed. What is this one?
Okay. The first one, the one that you have on your hand, is the first prototype. In fact, the microcontroller used is chosen also because it is a commercial device that is a wide availability and is also implemented in developed board. And therefore, for an easy development process, I've started the process using a standalone devices that I'm sure that the hardware is not a problem. and I'm based all my attention on the firmware. Then, when the firmware works, I've tried to design my embedded devices with only the components required for the application, and which is yes, this is the device that is not mounted, and the official device at the moment is in Portugal because the rider needs to train itself. So, okay, but the second one is the official device.
Other questions? Okay, thank you again.
Thank you.
Okay, the second candidate is Carboni Giovanni, and the title of his thesis is High Bandwidth, High Gain, Beam Steering Antenna Design for Automotive Internet SATCOM in the Framework of LEO Satellites.
So, good morning. My name is Giovanni Carboni, and today I will present the results of my collaboration with the research and development team of ASK Industries, which consists in the design of an high bandwidth, high gain, and beam steering antenna for the automotive internet SATCOM in the framework of the low Earth orbit satellites. This is an on-the-edge topic, since the only available similar technology is owned by Starlink, which is only suitable for houses and not for any type of vehicle. Well, this is the outline of my presentation. First, it will go through all the constraints and requirements in terms of the automotive and satellite environments. Then I will present the link budget calculation I carried out in order to understand what is the minimum required gain by the antenna. Then I will go through a description of the individual element that will compose the array in terms of both the architectural choices and the simulated results. Then I will propose two different array configurations and the relative results, and then conclusion follows. For what concerns the automotive constraints, considering the fact that the antenna should be as invisible as possible, only low-profile technology can be used. In addition to that, we require that the antenna should radiate only upwards, and so the only technology that is able to meet both these two requirements is the patch antenna. There is a widespread technology among the printed ones. The LEO satellite constraints are mainly four. First of all, satellite communication exploit only circular polarization that is able to provide resistance to multipath fading, polarization mismatches, and also to atmospheric attenuation. The second constraint is about the bandwidth. In particular, the ITU agency has allocated a particular range of frequencies for this type of communication. That is between 17.7 and 21.2 gigahertz, resulting in a 16.5% of bandwidth, which is a relatively challenging requirement for patch antennas. The third requirement is about the distance between the vehicle and the satellite. In particular, this thesis aims at designing an antenna that is able to reach up to 1,000 kilometers far satellite, but it could be easily extendable to reach up to 1,500 kilometers. The last requirement is about beam steering. If you consider, for example, that at t equals t1, the satellite is at position equals to theta 1, and at t equals t2, the satellite is at position theta 2, then you can easily imagine that the antenna should be able to modify electronically the direction of the main beam in order to be able to reach the satellite regardless of its position in the sky. As a result, plus or minus 30 degrees of scanning angle is required for this antenna. Well, for what concerns the link budget analysis, I started considering the situation where the satellite is perfectly aligned vertically with the vehicle, and adding together both the path loss that a wave is naturally subjected to and the atmospheric attenuation. For the angle 0, we have calculated the starting attenuation. But we have to consider that when the satellite is at a given position, so when the angle is different from 0, the distance between the vehicle and the satellite is increased, and so the losses are higher, resulting in an increasing trend in the plot. So, considering as previously said, the 1,000 kilometers of orbit with an angle of 30 degrees, a total attenuation of 180 dB is calculated. So, solving Frisch's formula with respect to the required gain, it turns out that a minimum gain of 15 dB is required. Then, summarizing, the final array will be a 4x4 array, circularly polarized, able to reach up to 1,000 kilometers satellites of orbits, beam steerable, and wideband. Well, this will be the final structure, but let's first consider one single element. It will be described in terms of feeding mechanism, its stack-up configuration, how we have achieved the circular polarization, and the simulated results. The reasoning that brought us to the final architecture started considering that patch antennas generally have a much lower bandwidth with respect to our requirements. Nevertheless, the easiest way to increase the bandwidth of a patch antenna is to increase the substrate height. Indeed, as you can see here, a thicker substrate is associated with a larger bandwidth, but a thick substrate gives rise to the so-called superficial waves that, in the radiation pattern, basically disrupt completely the trend of the gain, resulting in an unwanted behavior. So, we have decided to substitute the dielectric material with air. Air, on the one hand, provided a larger bandwidth, sustaining no superficial waves, but on the other hand, of course, only a particular type of electromagnetic coupling is possible to feed the antenna. Indeed, the final structure will be a patch antenna sustained by a stop layer on top. The cavity here is the substrate and is made of air, which is surrounded by aluminum. The aluminum, in the array configuration, should be able to reduce the cross-talking between the adjacent elements in the array. Below it, onto a layer of copper, two slots have been obtained, these two. These slots should let the microstrip couple with the patch, letting it radiate toward the satellite. In order to achieve circular polarization, if the signals coming into the two microstrips are out of phase of 90 degrees, the resulting electric field rotates, resulting in circular polarization. Well, for what concerns the results, let's talk about the impedance matching first. If we consider a two-port network as our antenna, the matching is quantified by means of the reflection coefficient. It is defined as the ratio between the power exiting and the one entering one port. And as you may imagine, it should be as low as possible. And in particular, the rule of thumb is that it should be lower than minus 10 dB. And indeed, the results of the simulation shows that the antenna is perfectly matched over the whole bandwidth. For what concerns the radiation pattern, we can see that the antenna radiates mainly upwards as expected with a gain of 7 dB, but the presence of the slot in this particular type of configuration increases a little the back lobe here, resulting in a little bit of reduction in the radiation towards the main direction. To quantify the purity of the polarization, let's first consider a rotating electric field and its component along the x and y directions. In order to obtain circular polarization, the conditions are that the two components must be equal and out of phase of a multiple of pi half. The axial ratio, there is a figures of merit, quantifies the deviation from these two conditions. So, the lower the axial ratio, the better the polarization. Indeed, as a rule of thumb, an axial ratio lower than 3 dB is considered a good result. This is the first array configuration that I have simulated. As you can see, the single element is just rigidly repeated 16 times in order to obtain a 4x4 array. Results are shown in terms of impedance matching, radiation pattern, and axial ratio. Well, in an array configuration, the matching is quantified by means of the active reflection coefficient that takes into account also the coupling between different elements of the array. When the array is set to radiate towards the broadside direction, so when theta is equal to 0, what happens is that if we compare two different ports, one external and one internal of the array, we can see that the internal one is subjected to a matching worsening due to the surroundings. This, unfortunately, is something that designers cannot do anything about, unfortunately. And also, the active reflection coefficient is also depends also on the level of steering. In particular, if we look at the plot, we can see that different level of steering is associated with a different level of matching for the same point. To obtain the steering, by the way, the phased array theory is exploited. In particular, a progressive phase shift between elements of the same row is applied in order to incline the equiphase front of radiation, resulting in a radiation towards a specific direction different from the zero. For what concerns the radiation pattern, here we can see that the main radiation is towards the wanted direction, so the zero degree, with a gain of 17 dB. Unfortunately, this is not enough because despite it is greater than 15 dB, when steering is performed, the gain tends to reduce because of greater lobes here will show, resulting in a radiation with a gain that is lower than 15 dB. So this is a not so good result. Also, for what concerns the axial ratio, we can see that there are many directions for which the axial ratio does not satisfy the requirement. And indeed, we have simulated a lot of different configurations, but the one that's shown the best results is the one presented here. As you can see, is obtained taking some elements, like for example these four, and rotate them in order to obtain a more symmetrical structure. Indeed, this is symmetric with respect to both the axes. As we will see in a few, this symmetry is a key parameter in order to obtain the best performance. For what concerns the active reflection coefficient, unfortunately, we can see that almost the same worsening of the matching is observed here. But once again, it is something that we cannot do much about. But the best results are shown in terms of gain and axial ratio. In particular, we can see that the radiation is, as before, towards the main direction, toward the required direction, but now the gain is 19 dB, so 2 dB higher. This means that now we have the required margin to stay above the specification of 15 dB over the whole range of scanning angles. Also, the axial ratio is better. If you can see, we have a 10 to the minus 5 here. So basically, the axial ratio is substantially perfect for the broadside direction. Also, for substantially all the different directions, the axial ratio is below the specification, except for one direction, which is theta equals to minus 40, unfortunately. But considering the fact that in the future, the number of satellites in the orbit will be much higher than now, lower values of scanning angle will be required. And so we can consider that the antenna is substantially satisfying all the constraints. Well, to conclude, the goal was to design a low-profile phased array antenna to be mounted on the roof of a vehicle, able to communicate with low Earth orbit satellite. In the design steps, I focused my attention first on determining the link budget in order to calculate the minimum gain required by the antenna to communicate properly. Then, I concentrate in designing a non-existing aperture-coupled patch configuration in order to satisfy the requirements in terms of circular polarization. And then I put this single element into an array configuration able to reach the requirements in terms of gain and axial ratio bandwidth. Indeed, all the specifications have been achieved, such as we have overcome the required gain in terms of link budget with a full axial ratio bandwidth, and the final structure is of 7 mm of thickness, which can be classified as a very low profile structure with almost plus or minus 40 degree of scanning angle. Thanks for your attention.
Thank you, Giovanni. Questions?
Yes.
It's a curiosity. I mean, in the near future, the market of LEO satellites is going to become important, and there are, I mean, some experiments being conducted with LoRa, for instance, for a satellite IoT or something like that.
Yes.
Did you give a look at the commercial market? I mean, how does this project compare with maybe similar related products, or I don't know?
About the LEO satellite in general.
Yeah. So I don't know if there are antennas available on the market for this application or not, or.
Well, all the satellites that are in orbit now are owned by three main companies. Mm-hmm. The one is Starlink, which is the one that owns the highest number of satellite. And I think all the technology that is inside this satellite is classified, I think, and they develop all inside. So we don't know much about it.
Okay, so maybe there are some patents or something which is...
Yes, I think so. So.
Thanks.
Other questions? Yes.
Actually, just a curiosity about the S11.
Yes.
The problem. Would it help to separate better the different parts of the array, and what would be the cons, let's say?
Yes, actually, in one of the we have tried many solutions trying to separate the different elements in order to, as you said, trying to isolate the different elements and reduce the crosstalking between them. But the results were not so good, and actually we tried before trying the symmetrical structure. So maybe a combination of the two solutions would be the best solution in order to improve further the matching, of course.
Okay. Thank you again. Okay, the third candidate is Prattisoli Angelica, and the title of her thesis is Transverse Roughness Effect on Loss of Hollow-core Inhibited Coupling Tube Lattice Fibers.
Okay. Prova. So, hi, I'm Angelica, and today I will present you a research work on the roughness effect on loss included into the European project CRISCube. This is the outline of my presentation. Firstly, the context is introduced, and the guidance mechanism is explained. Then, we will see a few numerical results, starting from the creation of an analytical model, which will be applied to the fiber by tuning some parameter to study the roughness effect. Sorry. Now, at the top, we can see the evolution trend and the new record loss limits achieved by photonic crystal fiber in the last years. The purple line represents the scattering limit for solid core fibers. Today, thanks to the creation of new technologies and the improvement in the fabrication process, it is possible to obtain loss levels that lie below the Rayleigh scattering imposed by silica. However, there still remains a gap between the theoretical value and the measured one, which turns out to be higher due to the presence of some additional losses. Among the several existing geometries, we will see the tube lattice fiber composed by 8 non-touching tubes and a center hollow core. The reason for which this additional loss exists has not been so far clearly identified. One of the possible causes is the surface roughness, which is directly created during the fabrication process so that the tube surfaces will no more appear smooth, but affected by a small corrugation. The issue with these height variations is that they will cause an additional surface scattering loss, which, as we will see, is detrimental on the fiber performances. What makes my study interesting is the fact that the roughness along the transverse direction with respect to the propagation of light has never been investigated before in literature. The roughness effects are highly correlated with the guidance mechanism, which therefore is necessary to briefly recall. In the inhibited coupling, the core modes can exist in a continuum of cladding modes. Looking at the spectrum, we can recognize two different regions. The low loss regions, which are the transmission bands, separated by high loss peaks. These high loss peaks happening at certain wavelength are generated by the coupling between the core and the slow oscillating cladding modes. On the other hand, in the low loss regions, even if there still exists a cladding mode, they are not coupled between the core mode, since we have fast oscillations. Now, the roughness plays the following role. It enhances an unwanted coupling between the core and the cladding modes. This fact explains why the fiber affected by roughness show higher losses level. The higher the roughness, the greater the impact. Therefore, in order to improve the fiber performances, the control of this perturbation is mandatory. We can easily see that the roughness is a stochastic process with a certain power spectral density S. Therefore, in order to model it, we have built an analytical model taking into account that the displacement, dr, is described as a sum of independent, random, and cosinusoidal functions, which are 2π periodic with the circumference. These harmonics depend on the root mean square value RMS, on the power spectral density PSD, and on the randomic phase constant. My transverse roughness study is divided into 2 points. The first one relies on the coupling effect between the core and the cladding modes. And the second one quantifies how strong it is, this coupling, which is characterized by the trend of the PSD. Now, starting from the coupling effect, regardless the shape of the PSD, we have firstly considered the simplest case of a constant PSD, which is applied at two fibers with different dimensions. Fiber 1 having a smaller core diameter than fiber 2. The two graphs show the loss trend in function of a normalized parameter given by the thickness of the tube over the wavelength, given by the thickness of the tube over the wavelength. The colored line represents the roughness, the fiber affected by roughness, while the black dotted one represents the fiber without roughness, which is the ideal case. From the spectra, it is possible to deduce that the loss of the real fiber, the colored line, do not depend on the wavelength, and the loss increases with the RMS value. Moreover, the loss is inversely proportional to the core diameter of the fiber, as we can see from the comparison between fiber 1 and fiber 2 for the same RMS. Here, fiber 2, having a smaller core diameter, shows low loss levels. Finally, it is possible to observe that as the confinement loss of the ideal fiber progressively reduces, the displacement becomes more evident. In fact, by considering the black and the green line, when the confinement loss of the ideal fiber goes below the loss of the real one, since the latter is flat, it is possible to appreciate the roughness contribution. the highest loss enhancement happens in the short wavelength range. Here, the fourth transmission band. The roughness here is no more negligible. Now, having a constant PSD is a special case. Actually, the loss dependence on wavelength is due to the PSD trend. Therefore, consider a PSD which depend on the spatial frequency. Here, we have computed the losses by tuning the ratio between the circumference and the correlation length, while keeping constant the RMS value. Results show that the lower the confinement loss is, the lower the correlation length is, the higher the displacement is. The graph on the right bottom illustrates the displacement taken at the center of each transmission band. As expected, here we can see an increasing trend. An equivalent and complementary analysis has been performed by changing the RMS value while keeping constant the correlation length. Here, again, we can see a loss increase effect with higher RMS value. Also for this case, the displacement has been computed at the center of each transmission band, showing an increasing trend. Now, in this slide, I report a summary on what has been stated before to take a further consideration. Here, we can easily see that displacement obtained by a variable RMS reaches higher values than the displacement with a variable correlation length. The reason for this effect can only be explained by the fact that the transverse roughness effect are highly correlated with the PSD trend at higher spatial frequencies. As a proof, we have considered two PSD with different shapes. We have a quadratic dependence, the blue line, which is dominant at lower frequencies, and a linear dependence, the red line, which is dominant at higher spatial frequencies. Results coming from the simulation prove that the effect loss are greater for the red plot, which is dominant, corresponds to the PSD dominant at higher spatial frequencies. Therefore, the hypothesis we have made before, for which the transverse roughness effect are highly and mainly driven by the PSD spectral content at high spatial frequency, is true. So in conclusion, we have deeply analyzed the transverse roughness effect, which has never been investigated, by taking into account an analytical and numeric approach. Results show that the loss is inversely proportional to the fiber size. The roughness impact is proportional to the RMS value and the inverse of the correlation length, and the loss is mainly driven by the PSD at high spatial frequencies. Thank you.
Well,
very interesting study, thank you. Okay, the loss is very high in the highest pass bands, let's say. But if I remember correctly, your vertical scale is log, and you end up having, yeah, this for instance is just one example, but there was even another one before where you had 10 to the, or even 10 to the 5, I think, somewhere. So even in the lower pass bands, I would say it's not totally negligible.
Yes,
would you agree on that? Yeah.
Mm-hmm. Yes, I mean.
Yeah, that was the one I had in mind,
yes,
exactly.
Yes. Here we have considered a constant PSD to show that the displacement becomes no more negligible, but we can see that even here it is not negligible.
Yeah.
Actually, as the confinement loss of the ideal fiber progressively lowers, the effect becomes greater.
But the sigma you are considering are realistic? Have been measured on the actual fibers?
They are realistic. Yes,
okay.
they are realistic.
Okay. And another curiosity, can you go back to your first expression of the roughness, how you put it into the model? Exactly. So basically, you randomize the angle, but you keep the n theta because you want to avoid discontinuities. I mean, that roughness must be a perturbation that changes with the angle,
yes,
right?
Yes, with theta. Yes.
So the cosine function, however, is always n times the theta and is fixed.
Yes, because n is this is the number of harmonics. So the roughness depends also on the number of harmonics, which appears at this power spectral density. And the dependence on the theta is inside the cosine function.
Exactly. And the delta R as a function of theta is continuous as you close. That's my point.
Yes.
Okay.
It is 2 pi periodic with the circumference. Yes.
Okay. And what about randomness in the axial direction?
Oh, okay. This is, we have only considered the transverse direction. So we have cut a section of the fiber and we just considered it in the 2D plane.
So essentially it's a cylindrical type of thing. Okay. Anyway, very interesting because there are similarities with the scattering of electrons at the surface of MOSFETs. You have roughness there too, and if you treat electrons as quantum waves, you end up with similar things. Thank you.
Okay, other questions? Okay, no, so thank you again. Okay, the next candidate is Solly Elena, and the title of the thesis is Effects of Non-Idealities on Hollow Core Inhibited Coupling Tube Lattice Fibers.
Provo. Okay, so good morning. My name is Elena. The title of my thesis is Effects of Non-Idealities on Hollow Core Inhibited Coupling Tube Lattice Fibers. This thesis is framed in the context of the European Cube, which is aimed at the creation of a new platform for quantum sensors based on these type of fibers. My contribution consists in the study of their non-idealities. Firstly, this is my presentation. I will start by providing you with a brief introduction on the main characteristics of these fibers and of their non-idealities. Then I will explain to you the model I have created in collaboration with the fibers to study these non-idealities. I can take it off. No. Does it work like this? Okay, thank you. Okay, so as I was saying, firstly, I will describe to you the main characteristics of fibers. Thank you. Okay, so firstly, I will describe to you the main characteristics of the type of fibers. Then I will explain to you the model I have created in collaboration with the FEMLab to of the non-idealities. I have studied two types of non-idealities, namely fiber tilting and fiber twisting. So for both of them, I've studied the dependency of their effects on the normalized frequency and on the intensity of the non-ideality. Then I've studied the influence of the geometrical parameters of the fiber. At the end, I will conclude my presentation by briefly comparing the two non-idealities. So let's start by describing the characteristics of the fibers. Hollow core fibers are constituted by an external glass tube filled with smaller cladding tubes. They are micrometer sized and arranged to leave a hole in the middle. More specifically, I have created one model for each non-ideality. The purpose was to numerically quantify the effects of these non-idealities. The first non-ideality I have studied is fiber tilting, which basically corresponds to the tilting of the fiber axis of a certain angle indicated in red here. The second non-ideality is fiber twisting, which basically corresponds to the rigid rotation of the cladding tubes. Once again, the angle specifies how strong the effects of the non-idealities are. So, to better understand how to quantify the coupling, we should look at this phenomena from another point of view. So, this is the fiber cross-section immediately before the non-ideality. And the blue rectangle represents the power of the fundamental mode. Immediately after the non-ideality, we see that the power of the fundamental mode has been reduced and that the contribution of new modes appear. The amount of power lost by the fundamental mode is what we are trying to quantify. To do so, we should study the coupling between the fundamental mode before the non-ideality and itself immediately after. If we take the overlap integral C and calculate this quantity, namely 1 minus the square of the fundamental mode, we find a value which is the percentage of power lost by the fundamental mode with respect to its initial quantity. If we said we want to quantify the amount of power gained by each mode in the second segment, we should study the coupling of the fundamental mode with a generic mode J. We calculate the overlap integral and then compute its square value. By doing so, we obtain the percentage of power gained by mode J with respect to the initial power of the fundamental mode. So these two parameters, 1 minus c squared and c squared, have been calculated for a huge amount of fibers. These are just some examples, and I have reported them here to give you an idea. Before moving on to the results section, I would like to recall the definition of normalized frequency, as it will appear several times in the following slides. So normalized frequency is a dimensionless quantity which is exploited to compare fibers of different dimensions consistently. As you can see, in fact, the wavelength lambda is normalized with respect to T, which is the thickness of the cladding tubes indicated here. N glass and N air are, in this case, the refractive indices of the material composing the tubes and the material composing the air, respectively. So let's start by describing the results of the tilting of the fiber axis. Here on the plot you can see c squared as a function of the normalized frequency for 5 different modes indicated here. Firstly, as we said before, the value of c squared is proportional to the amount of power gained by each mode. You can clearly see that c squared depends on the mode, namely the curves are not overlapped and every mode gains a different amount of power. C squared also clearly depends on the frequency. We can see that not all curves have the same slope. In fact, the red curve and the green curves have a higher slope. By repeating the simulation of these parameters on a huge amount of fibers, I could formulate scaling laws. There is one first mode packet for which the value of c squared is proportional to the square value of the normalized frequency, such as these first curves here. Instead, there is a second mode packet for which the value of c squared is proportional to f to the power of 4, namely the red curve and the green curve. The second interesting dependency was the one on the tilting angle. Here you can see once again the value of c squared as a function of the normalized frequency for the same 5 modes of before for 2 different tilting angles. The angles differ of 1 order of magnitude. Okay, firstly we can clearly see that the values of c squared increase for increasing angle. More specifically, if we focus our attention on the pink curve, we see that for an increase of 1 order of magnitude in the angle, we see an increase of 2 orders of magnitude in the value of c squared. This is not the same for all the curves, and if we consider the red curve, we notice an increase of 4 orders of magnitude. Once again, simulations have been repeated several times and scaling laws have been formulated. For the first mode packet, the value of c squared is proportional to 5 to the power of 2, whereas for the second mode packet, it is proportional to 5 to the power of 4. Okay, the last results concerning fiber tilting are those concerning the influence of the geometrical parameters. The only parameter which showed a significant effect on the tilting losses is the core radius in this case, indicated here in the figure. So on the left we can see the values of the 1 minus c squared of the fundamental mode as a function of the core radius. As previously said, 1 minus c squared of the fundamental mode is proportional and indicates the amount of power lost by the fundamental mode. We can clearly see that this parameter increases with increasing core radius. More specifically, it is proportional to it. Once again, a scaling law has been found. This happens because because the tilting non-ideality distorts the center of the fiber, the core region. So if we increase the core, we are increasing the amount of distorted area, and therefore the power losses increase. Okay, let's go to the second non-ideality, namely fiber twisting, the rotation of the cladding tubes. On the left, you can see 1 minus c squared of the fundamental mode as a function of the normalized frequency for 4 values of the twisting angle, phi. As before, 1 minus c squared of the fundamental mode is proportional to the power lost by the fundamental mode. We can clearly see that the curves are flat in this case. So 1 minus c squared does not depend on the normalized frequency. It instead depends significantly on the twisting angle. More specifically, it has a square value dependence. Okay, concerning the geometrical parameters of the fibers, a study concerning the effects of tube gap has been conducted. So, the tube gap is the minimum distance between two cladding tubes, as indicated here. On the left, you can see 1 minus the square of the fundamental mode as a function of the twisting angle for 4 different fibers having 4 different gaps. The pink curve, which is the highest one, corresponds to this fiber, which has a pretty big gap. Instead, the orange curve, the one at the bottom, corresponds to a fiber having very small gaps. As you can see, the tubes are almost touching. So, in this case, the scaling law which has been found is that 1 minus the square of the fundamental mode is proportional to the square root of the tube gap. But the interesting point is the physical meaning. So, when the gap is big, the electric field profile has a polygonal shape. Instead, when the tube gap is small, it has a round shape. As you can clearly imagine, a round shape is less sensible to the rotation of the tubes, whereas a polygonal shape is influenced a lot. For this reason, rounder shapes have lower losses. Okay, so this is the last geometrical parameter I have studied, which is the core radius in the case of fiber twisting. On the left, you can see, once again, 1 minus the square of the fundamental mode as a function of the twisting angle phi for 3 different fibers having 3 different cores. Differently from fiber tilting, in this case, when we increase the core radius, the power lost by the fundamental mode decreases. So this is the opposite trend as before. This happens because, in this case, when we increase the core radius, the shape of the electric field profile becomes rounder. And, as we said before, a round shape is less sensible to the twisting. In this case, the scaling law is that 1 minus the square of the fundamental mode is proportional to the inverse of the core radius. This happens because the twisting acts more in the cladding tube region and not in the center. So to conclude, I would like to recap my contribution and the main results. So firstly, for the very first time, these non-idealities have been included inside the model of a fiber. More specifically, one model for each non-ideality has been created and then deployed to conduct simulation campaigns to numerically estimate the effects of 2 non-idealities, namely fiber tilting and fiber twisting. As we could imagine, both depend on the intensity of the non-ideality, namely on the angle. Whereas, just fiber tilting depends on the normalized frequency. For what concerns geometrical parameters, we have found opposite trends in the case of the core radius. This is because fiber tilting acts in the center of the fiber, whereas fiber twisting acts in the tube regions. The last dependency is the one on the tube gap, which is non-existent for the case of fiber tilting and of square root type in the case of fiber twisting. With this, I have concluded my presentation, and I thank you a lot for your attention.
Thank you. Questions? No questions? Okay.
Sorry, I'm the bad guy today, obviously. No, it's interesting that you extracted some scaling laws for all these. However, I never saw in your graphs a theoretical trend corresponding to. So, can you give us some number or some, comment on what the error between the theoretical curve and the numerical simulation is?
So, firstly, I have to say that it is unfeasible to directly measure these non-idealities. So, thank you. So, having real curves to be compared with difficult. Nevertheless, the losses are measured by a partner which collaborates with the CRISCube project. And what has been found is that there is a systematic difference between the measured losses and the simulated ones when the model does not include the non-idealities. So what we know up to now is that if we do not include non-idealities in the model, the real curves are different with respect to the simulated ones. So the idea is to try to understand which non-idealities have the biggest impact, to try to include them inside the model, and then to see whether there is matching. So this is the first step to do so.
So thank you again. Okay, the next candidate is Sonalia Daniele, and the title of his thesis is Cyber Risk Analysis and Secure Design of an Industrial Network Architecture.
Prova? Si sente? Okay. Hello everyone, my name is Daniele Sonaglia, and today I'm going to present you my work, a cyber risk analysis and a secure design of an industrial network architecture. I developed this work together with System Logistics, a company that produces automated warehouses. In particular, you can see in pictures, it produces a broad range of machines, such as conveyors, stacker cranes, and autonomous guided vehicles. In particular, I worked in the electrical technical office for 6 months. We are in the setting of Industry 4.0, where smart automation and connectivity takes place. But with the advantages brought by connectivity, also cybersecurity risks come into play. So the goal of the company was to design a secure network architecture for these machines that had compliance to the IEC 62443 standard. The steps that I followed in my projects were two. First of all, I developed a state-of-the-art about the latest industrial networking protocols and cybersecurity measures, and then I applied these measures to a project, to a pilot project of System Logistics. The things that I looked at in my research phase are, first of all, a brief introduction about the industrial networking protocols that were used there, ASI, Modbus, and Profinet. ASI is a communication protocol that works over power line, so here the cybersecurity aspect was not preponderant. Instead, it was more about reliability and quality. Instead, with Modbus and Profinet, that are two protocols that belong to the Ethernet world, here cybersecurity aspects were more relevant. In fact, these two protocols can be attacked by industrial malwares, such as Stuxnet, ECANS, and Pipedream. These malwares are able to halt the production or even changing the PLC codes, generating dangerous behavior for the machines. Therefore, I addressed the cybersecurity matter with this standard that mandated, first of all, a risk assessment, and then stated some system requirements that needed to be respected. This one is the network of the project that I worked on. It's the System Logistics warehouse, and being System Logistics a company that produces automated warehouse, its warehouse has all the newest features and all the tests and functionalities are present. So I worked in this warehouse that's made by 5 areas. First, a stacker crane warehouse where basically the heaviest mechanical parts are located. A smaller part and electrical part warehouse that's called LogiMate. Then 2 test areas that I developed my application on. And then a last subnet for the autonomous guided vehicles that roam all over the plant. These are the steps that I developed on the project. First of all, I performed an asset inventory of all the network. Then I performed a risk assessment. And on the basis of the outcome of the risk assessment, I designed the security measures. These are the tools that I adopted to perform the asset inventory. First of all, I started with Wireshark. That's a passive network analyzer. Basically, connecting to a mirror port, we are able to infer things such as the source IPs and destination, packets, data flow, data rate, etc. The second tool is Nmap. It's an active network scanner that basically sends packets to a device, and based on the answer of these devices, it can infer things such as the softwares that run on open TCP/IP ports, or even the operating system of these devices. The last tool is PNT tool. That's a tool in use by the company developed by the University of Brescia that interacts with Profinet, one of the 3 protocols that I mentioned in the beginning, and it allows for the creation of a network topology, such as the one in figure, and it gathers punctual information of the device. Putting together the results of these 3 tools, I developed a table with all the description, the hardware, the firmware, and all the information needed to perform a risk assessment. The next step, in fact, was a risk assessment where I grouped all the devices together in order to understand at low level which were the areas that needed more security. And on the basis of the threat, consequence, likelihood, and severity, the areas that were classified with a risk higher than 6 have gone throughout a detailed risk assessment. A detailed risk assessment consists in the study of the vulnerabilities. Vulnerabilities are the weak points that a networked device has. In particular, we are working mostly with Siemens devices in system logistics, so a huge list of vulnerabilities were present. Usually, these vulnerabilities are listed in a national vulnerability database kept by the US government, but thanks to a tool developed by Chris by Unimore, I have been able to organize them better and to understand which were the criticalities that had a more higher score. Then, on the most critical vulnerabilities, I've identified some workarounds that, together with the standard requirements, were the basis for the design of the secure network. I will just present you now 2 key examples to make you understand what a vulnerability is and which type of requirements were asked for. A vulnerability, for instance, this one is a vulnerability of a Siemens PLC that states if a large amount of packets, of Profinet DCP packets with those characteristics, a given header type and a given frame ID, arrive to the PLC, then this PLC may halt. So a security measure that I implemented was the one to block these packets when not needed. Instead, an example of system security requirement was there was the need to uniquely identify and authenticate all the users engaged in wireless communication, for instance, all the autonomous guided vehicles clients. And in this case, I implemented a MAC address control list thanks to whitelisting and blacklisting the MAC addresses of the devices that were needed or not. This type of reasoning then has been applied to the whole network, and the outcome was the design of this new network architecture that we can see on the right. In particular, there are 4 main points that we need to respect, summing up all the requirements, that are, first of all, hardware and software compliance in terms of development and in the terms of new hardware buying. So basically, first, a cost analysis network architecture has been performed. So we needed to pay attention to the costs, basically. Then 3 more technical concepts have been introduced. The concept of segmentation. Basically, we render the network smaller in order to put different cybersecurity requirements on different areas. For instance, if we have an area that needs quickness of response and performance, we will put less cybersecurity requirements there because, for instance, if we need the machines of that area to be stopped when an emergency button is pressed, the response needs to be quick and fast. And this is the safe VLAN, for instance. Instead, we can see the external vendor VLAN. Here, cybersecurity requirements are more stringent because we do not know what's exactly in there being from other vendors. So here, cybersecurity requirements are stronger at the expense of the performance. Then the communication between these areas has to be managed, and we did this in particular employing 2 firewalls, Siemens SC632, that basically, based on the protocols that can cross or not the network, we inserted some firewalling rules. For instance, such as the one that I mentioned, you blocking the Profinet DCP packets for given devices and given EPs. Lastly, a tool for the diagnosis has been inserted. That is the IoT 2040 tool. It is a Siemens programmable device working on Linux that basically performs protocol analysis. It combines the functionalities of the Wireshark and PNT tool, and it allows for the networking engineers to gather information about the network, quickly troubleshoot, and
even doing so in a remote way. But what was the point of developing this new network architecture? Basically, before, the network was plain, simple, and unstructured, and all the packets were put together in one big network. Instead, doing segmentation and firewalling, we have been able to increase the security and the efficiency of the network. I mention also the efficiency because working with smaller networks, there is less chance for the packet collision, so less errors and retransmissions. The second point is that this network has been taken as a reference for the realization of System Logistics Future Plant. In fact, even though the cost increases, many more customers are starting to require cybersecurity measurements. Therefore, the implementation has been quickly started. Lastly, I want to state that the milestones achieved by this TC are not a point of arrival. Instead, are a starting point, and many more security measures, such as intrusion detection system, remote control, and log management servers can be inserted, hoping that the security will improve again, since it's a theme that's now currently keep going. This basically was my work, so I thank you all for your attention. And if there are any questions, please let me know.
Thank you. Questions? Okay, I just have a curiosity about the conclusion and the next step. You say there are several improvements.
Yes.
Because that one is just the first step of a longer work. What do you think? What is the most important or urgent improvement?
Actually,
So the first of the several steps.
Like, there is a say that basically the most dangerous thing for cybersecurity issues are people. So basically, the single guy that puts the key into the PC and spreads malware that has no awareness of cybersecurity. In general, from a technical point of view, we can state that all the measurements have to be followed constantly. So it's not just something that you implement, but there has to be a work of updating the devices, updating the tools, understanding which are the new vulnerabilities that every day are listed, new vulnerabilities for the devices are discovered, and each one of them has to be addressed. So it's very broad range theme that has many different applications, but the point is that it's a thing that has to be controlled in terms of improvement.
Okay, thank you. Again. Okay, the next candidate is Tondelli Lisa, and the title is, have the Italian title, effetti di autoriscaldamento nella tecnologia CMOS avanzata a 14 nanometri.
Un secondo, arrivo. Okay, good morning. The title of my thesis in English is Self-Heating Effects in Advanced 14 Nanometer FinFET CMOS Technology. My thesis has been in part developed together with an industrial partner which is specialized in semiconductor devices and circuits. I would like to start with some motivations at the basis of my thesis. The current trend in microelectronics consists in the miniaturization of MOS transistors and in the increase of the number of transistors per chip. This leads to an high integration density and power, and therefore to an excessive power dissipation per unit area. This, together with possibly inadequate dissipation pathways, could lead to the increase of MOS channel self-heating, and therefore devices could show degraded performance and therefore unreliable operation. This brought device designers to face self-heating effects and thermal management problems. This is especially true for two innovative MOSFET architectures which are used for ultimate integration in silicon, in particular a fully depleted SOI and FinFETs. We will mainly concentrate on FinFETs in the framework of this thesis. However, FD SOI looks as conventional MOSFETs, therefore there is the source, the drain, and the channel in between where the electron flows. Above the channel there is the gate, and the entire structure will sit on an ultra-thin barium oxide layer, which is an insulating layer, so having a low thermal conductivity, which will not facilitate the heat dissipation. When we move to the other solution, so the FinFET, we can see instead that the source and drain are vertically lifted, and therefore we can see this very thin fin in which the current flows. In the perpendicular direction, there is the gate, which is also named the finger. In this case, the heat dissipation will happen through this very thin fin, and therefore it will not facilitate it also in this case. Now, I would like to provide to you some ideas on the origin of self-heating, and this is done based on the conventional planar structure of the MOSFET. In particular, the electrons are set in motion by the electric field, which moves from the source toward the drain. The electrons will accelerate and therefore gain kinetic energy, and the electron gas will heat up as a result. Collisions with the crystal lattice will start to cause loss in kinetic energy of the electrons, and therefore the lattice temperature increases as a result of the self-heating. This means that the hot spot turns out to be located on the drain side. Before going on, I would like to specify that we employed a simulator, which is a Centaurus, which is an advanced TCAD platform for 3D structures. We needed first to define the model, then we defined the device architectures, and finally we had the possibility to calibrate the device model. Concerning the model definition, the model is divided in many different sections. We will only concentrate on the physics and on the math. In the physics section, we had the possibility to study the transport model. There are three different possibilities: the drift diffusion model, in which no self-heating is considered; the thermodynamic model, in which the self-heating is exclusively considered in the lattice; and the hydrodynamic model, which is the most complete and therefore accounts also for the temperature of the carriers. Then we studied the ballistic mobility, which is introduced because we are working with transistors having a very short channel, and therefore the electrons will move with a ballistic model. However, we tried to remove the ballistic mobility from the thermodynamic model, and this could be seen that the effect is not so strong. However, this is due to the fact that the mobility is affected by many different parameters, and therefore the ballistic mobility is just one of the different ones. The last parameter we investigated is the velocity saturation, which, however, will be presented later during the calibration. Concerning the math section instead, we had to choose the solver among three different possibilities. The solver will impact on the convergence and results of the simulations, and therefore we decided to choose, after many different tests, the ILS solver with optimized parameters. Now we have a model, and therefore we can define the different architectures that we employed. The first one is the easiest, and it is the single finger, single fin device. This is the fin, and the other one, moving in the perpendicular direction, is the finger. By putting multiple of these structures in parallel, we can obtain the multi-fin single finger device, in which multiple fins are set in parallel and will share the same finger. Again, there is an additional improvement, which is the multi-fin, multi-finger, in which multiple of these structures are put in parallel in the opposite direction. So we have that this one will turn out to be this structure. While moving from left to right, we have an increasing complexity, an increasing number of mesh elements, and therefore also increasing simulation times. The first model could therefore be used for the model calibration, the second one for the optimization of the mesh, while the third one could only be used for the device analysis. Moreover, we also exploited a layout being shared by the industrial partner to define the reference cell that we will be using during the thesis. On this structure, we introduced two variations to reduce the self-heating effects and improve the dissipation pathways. The first one consists in increasing the CGP distance, so the distance among two following fingers. and the second one regards the introduction of a guard ring around the active device. Before moving to the calibration, it is worth mentioning the main differences being present among the two main transport models, so the thermodynamic and the hydrodynamic. In particular, we can see that the hydrodynamic shows a higher current, a higher output conductance, and a higher temperature with respect to the thermodynamic. Moreover, there is also a difference in how the temperature is distributed inside the structure. So we can see that due to the fact that in the hydrodynamic model, the electron temperature is larger with respect to the lattice temperature, we can see that the hot spot is wider, and it is also more displaced the drain side with respect to this thermodynamic model. And we also would like to understand whether this impacts on the thermal resistance of the device. The thermal resistance is evaluated as the difference in temperature divided by the dissipated power. The dissipated power is established by the current at all different bias points. As a result, the hydrodynamic model, which shows a higher current, will also show a higher a higher temperature. Nevertheless, the thermal resistance in the hydrodynamic case turns out to be lower with respect to the thermodynamic. After that all these differences has been announced, we can understand that due to the too large output conductance of the hydrodynamic model, we will discard this model in favor instead of the thermodynamic model. It is used here. However, when we compare it with the SPICE data provided by the industrial partner, we can understand that still some calibration is needed. Therefore, we started changing structural parameters such as the work function, the gate length, the doping levels, but we also needed an additional change to adjust the output conductance. Therefore, we reduced the velocity saturation. The final result is very satisfactory, and it shows good agreement on all the curves. Now we have a device model which works, and we can move to the device analysis. First of all, we will consider the self-heating effects in the reference cell. Then we will introduce the first variation, and therefore we will study how the self-heating varies when the CGP is increased. And finally, we will study instead the effects of the introduction of the guard ring on the self-heating. So, when the reference cell is taken into consideration, we can see that the temperature follows the following profiles. So, when we take into consideration this structure, we will see that the temperature decays according to circular contour plots. However, in correspondence of the presence of the source, drain, and gate metallization, there is a variation of this trend due to the fact that they have a cooling effect. Moreover, if we take into consideration this figure, in which instead the active device with exposed fin is present, we can see that the peak temperature of each of the 24 channels is different. And therefore, we want to understand whether this has an effect on the thermal resistance. So we studied the thermal resistance, we computed it for each of the channels, and we could understand that the peak values of the thermal resistance could be found in the middle of the structure. While moving toward the edges of the device, we can see an essentially monotonic decrease toward the edges. So what we concluded is that the thermal resistance is higher with respect where the outward heat flux is lower, so in the center. Now we can move to the first variation, and therefore to the version in which the CGP is increased from 90 nanometers up to 130 nanometers. In this case, what we expect to see is a heat reduction due to the fact that we will increase the distance among the fingers, which are the main heat sources, and therefore we expect to reduce the power dissipation per unit area. This could be observed both here, where a significant temperature decrease is measured, but it can also be observed in the perpendicular direction. Finally, the last variation is studied. In this case, we introduce the guard ring in this structure, so the two structures are exactly the same. The metals are lifted to make room for the guard ring, which is introduced just in the second case. What we can see from these temperature plots is that the guard ring does not impact so much on the maximum temperature, which is measured in the core of the active device. This is due to the fact that it is too far, and therefore it will just reduce the temperature when it is already too low. So this means that to increase its effect, we have the possibility both to make it closer to the active device or to connect it to the source. Finally, I would also like to present to you the heat dissipation in these complex structures. In particular, if we cut the structure along the finger, we can see that the heat preferentially dissipates in the vertical direction and in the fin direction. This is also highlighted in this figure, where this on the background is the fin, which is realized in silicon, and we can see that the temperature, the heat tends to reduce while dissipating inside the fin. The same could be observed in this case when the structure is cut along the fin, so these vertical lines are the fins, and we can see that the heat preferentially dissipates in the vertical direction, and therefore inside the fin and then inside the silicon substrate. Now I would like to conclude and therefore to present what we did during these months. In particular, we found a computational model for ultra-scaled FinFET devices. We studied the physical models and therefore the calibration of the device, and moreover we also investigated the solver robustness and the computational efficiency. We performed also a comparative study on device structures. We started from idealized single-fin, single-finger devices, and we arrived to realistic multi-fin, multi-finger devices. We also introduced the variation to improve the thermal resistance, and therefore we performed a thermal analysis, and we drawn some conclusion on the thermal resistance. First, increasing the CGP, which entails an important reduction, and then adding p-doped floating guard ring, which, however, introduces just a small variation. Concerning the future perspective, as I was already mentioning, we wanted to connect the guard ring to the source, and moreover, we would also like to develop an accurate thermal compact model to study how the temperature decreases and varies inside the structure. Thank you for your attention.
Thank you. Questions?
Lisa, as I'm a total foreigner to the type of subjects you were investigating during your thesis, I have a question regarding the tools that you are using, and specifically about the simulative tools. Do these elements, do these tools allow you to set the confidence intervals of the results that you obtain, or is a sort of automatic reasoning that the tool performs?
It is an automatic thing, so we could not set it.
Okay, thank you.
Okay.
Other questions? No? So, thanks again.
Okay.
Okay, now we have the last candidate, Vignoli Lia. He will have the opportunity to read in English his title because I have the only Italian one. Sviluppo di un cancellatore attivo di rumore basato sul processore ADSP SC589.
Prova. Okay. Hi everyone, my name is Elia Vignoli, and today I present my thesis, which is called Development of an Active Noise Canceller based on an IDSP SC589 processor. So during this presentation, we are going to see a small introduction about active noise cancellation. Then we will talk about the employed hardware, especially the ones that I use in my project. Then we will talk about the architectural improvement that I made. Then I will present you the storage strategy that I've chosen, as well as the accelerometer implementation. Then we'll talk about the multi-core communication that I implemented, and I will draw some conclusions. This thesis work has been carried out in collaboration with CNH Industrial and Analog Devices. So, acoustic noise cancellation can be obtained by considering passive methods, which are the most classical ones, and they typically they can be obtained by using acoustic insulation or barriers. The main advantages of these techniques are related to the low cost and to the simpleness, but the main disadvantage is related to the poor performances at low frequency. Therefore, also active methods have been developed, and typically they rely on active noise cancellation systems. The advantages are related to the high flexibility and high performances, especially at low frequency. The disadvantages are related to the complexity and to the cost of the systems. Talking about active noise cancellation, well, active noise cancellation is a quite old idea. Indeed, you can find results in literature dating decades ago. But the problem at that point was that the technology was not ready to implement such systems. Instead, in recent years, the availability of very powerful signal processing devices, such as, for example, DSPs and FPGAs, allowed to have some implementations of these systems. Active noise cancellation relies on the principle of destructive interference, basically, which means that you want to cancel a primary noise waveform, and in order to do that, you want to generate an anti-noise which is equal to the primary noise, but 180 degrees dephased. So when the two signals sum each other, the residual noise is obtained. And in the optimum case, the residual noise is equal to 0. But how to generate the anti-noise? Well, since the anti-noise is strictly related to the noise, and the noise is time variant, you have to use time variant electronics. And the classical solution relies on adaptive filters in order to generate the anti-noise. This is a simple example of an active noise cancellation architecture implemented inside ADACT, which is the simplest case possible. As you see, we have two microphones, one which is placed close to the primary noise source, and another which is placed close to the output of the duct. These two signals are then fed into the ANC core, which is containing the adaptive filters and the optimization algorithms. At the output of the ANC, we have the anti-noise signal, which is expressed by Y of n, and this signal is then reproduced by the cancelling loudspeaker. This is a possible result. As you see, I fed this system, this model, with white noise, which is the blue line. And after the transient, you see that the red line, which is representing the error, so the residual noise, is approaching 0. And this is how the active noise cancellation systems are used. In particular, during my work, the goal was to build a prototype in order to acquire and save high-quality audio samples as long as 3D acceleration samples. This setup will be mounted on the cabin of industrial vehicles. Then the samples that are acquired will be used in order to create and evaluate an effective ANC algorithm in MATLAB environment. However, due to time limitations mainly, I basically concentrated in the development of the hardware backbone, let's say, of the project. In particular, the difficulties that I experienced were related to the limited quantity of documentation which was present, the limited quantity of examples or codes, and the very high complexity of the hardware devices that I used. In particular, talking about hardware devices, this is the first component, which is the most complex one, and it is the Shark audio module. It is a 3-core architecture, which has also on top some other chips. It is a very complicated board. Then I have the second one, which is the microphones evaluation board, which has on top 4 MEMS microphones, which are high-quality 20-bit precision microphones. Then I used an accelerometer evaluation board, which is basically a 3-axis MEMS accelerometer. with 16-bit precision and up to almost 7 kilohertz bandwidth. The automotive audio bus is a protocol, is a patent which has been created by Analog Devices, and it is used in this project, and in most general cases, it is used in order to carry high-quality real-time audio signals. In physical layer perspective, you can see the automotive audio bus as a simple untwisted unshielded twisted pair, which is particularly designed for automotive applications. An A2B implementation is shown in this slide. And I used, this is a capture from Sigma Studio, which is a software specifically designed to build A2B configurations. And as you see, here I have a master-slave architecture in which basically the master is represented by the Shark audio module. Instead, the slave is the microphone evaluation board. And because of this configuration, I was successfully able to listen and to validate the audio path. Then, talking about storage capability, I had to choose the right solution in order to meet the project requirements. And the solution was selected to be the SD card. First of all, I had to understand the secure digital protocol, obviously. Then I used the SPI mode in order to access the SD card. The SPI mode is a simplified method to access the SD cards, and so basically I implemented the SD card on a in a high-level fashion at the beginning by deploying Python code for the FT232H, which is simply a USB to SPI converter. Then I translated this high-level code, high-level implementation into a lower-level implementation by using C code, and in particular by exploiting the mobile storage interface, which is proprietary of the Shark audio module. And this is what basically the C function does. Then I implemented the accelerometer. As before, I concentrated myself at the beginning on a high-level implementation by accessing the accelerometer in polling mode. But the problem at this point was that some samples over time were lost. So I decided to exploit the FIFO mode. In particular, I decided to exploit the FIFOs which are present on the accelerometer in order to develop a new implementation, which in this case was successful. Then I translated this high-level implementation into a lower-level implementation with a C function, basically, embedding also this code inside the project. And then I performed some demo acquisitions. In particular, I mounted the accelerometer on a vineyard tractor and performing 6 different acquisitions. And in particular, I placed the accelerometer on the rear window and on the right window of the vineyard tractor, and in order to have the z-axis always orthogonal to the surface of the window. So we expect basically that the z-axis will be the one which is more sensitive to the vibrations of the windows. This is why here I show some results, but only for the z-axis, because it is the one which is more sensitive to the vibrations. And here I compare mode 1 with mode 3. And basically, you can see that the amplitude of the peaks here and here are different. In particular, here, some peaks arrive close to 1 G. Instead, here, we are limited to 0.5 G. And this is related basically to the motion of the tractor, because in mode 3, we are moving at 10 kilometers per hour. Basically, the accelerometer is able to capture the terrain shape. Also, I did some comparison between mode 1 and mode 4 in frequency domain. And the only difference between the two modes is related to the position of the sensor. And as you can see, we have peaks. Well, probably you do not see that, but I can tell you. We have peaks at 25 hertz both in mode 1 and in mode 4. And also we have the higher order harmonics. And these peaks are related to the engine rotation. So by exploiting the signal from the accelerometer, we can directly having access to the information about the engine sound. Then the last part of my thesis was related to the communication between cores. Why that? Because the core 1 was the core that actually had to acquire the audio stream. Instead, the core 0 is the core that manages the accelerometer, so acquires the accelerometer samples, and manages the storage. So basically, I had to perform a communication, to enable a communication between core 1 and core 0. So I did that by exploiting the L2 memory by means of the multi-core API. The multi-core API is a specification which is originally embedded inside the SC589, and you can access it by proper APIs. And basically, what I did also in this case was to create a C function in order to initialize the MC API, initialize the endpoints of the communication, and validate the communication. So at the end of this project, I was able to create the main blocks of the prototype, namely the block that manages the audio flow, the accelerometer, the storage, and the communication between multiple cores. Then some acquisitions has been performed in order to have an idea of the signals coming from the accelerometer. In the future, these blocks that up to now has been tested separately will be put together in order to develop and to obtain the final active noise cancellation prototype. Then some measurements and some acquisitions will be performed for both audio and acceleration samples, and this data will be used in order to design and implement an effective active noise cancellation algorithm. And this is the end of my presentation. Thank you.
Thank you. Questions?
First of all, congratulations for what you have done. I know that just simply design for the SD card is not so easy to manage. But I have just a question about accelerometer. Were they aimed at giving you a sort of signal for feeding the active noise cancellation algorithm? That is to say, you... Sorry.
Yes, okay. Okay. So basically, as many signals, as many information you get, as better your architecture will perform. So the idea is this one. Based on the results that are present in literature, we found that active noise cancellation systems relying just on microphones were not sufficiently they exhibit not sufficient performances for active noise cancellation inside the cabin of industrial vehicles, because there are some results related to automotive, but in cars, and in cars it is sufficient to have microphones, but since the environment inside a tractor is very complicated in terms of noise, the microphones are not enough. So we basically exploit the accelerometer information to couple it with the microphones in order to get as many data as possible and to develop an architecture which is, let's say, most complete and performant as possible. This is another, just another way to get more information from the system.
So was there any spectral region in which accelerometer were more significant?
Yes. The accelerometer sensor is very sensitive to low noise, to low frequencies. In particular, in my thesis, I reported some figures that clearly show that basically the accelerometer is useful between 0, but well, 0 is, and 200 hertz. Okay, so we plan to use this accelerometer for low frequency.
Just one final comment based on the experience and your test. Do you think that such a system will ever become more cost effective than just a pair of noise cancelling headphones?
Cost effective? I don't know, because this is well, in principle, when you think of headphones, active noise cancelled headphones, you think about something which has 2 microphones and 2 speakers. So here we are dealing with up to 16 microphones and 16 speakers. So obviously the price will be high. But in terms of security of the, in terms of safe of the driver, it is well, we forecast that in every tractor, in every industrial vehicle will be embedded this solution, because the market is forcing this trend. Some tractor producers are already implementing such techniques in the high-level, in the high-end tractors, in the high-end vehicles, and we plan that also in the future for all the segments will be placed. Obviously, this technology, in order to be cost-effective, needs to be requires basically an high time. It requires time, as every new technology. But yeah, this is the
strictly speaking, is obvious, but I mean, we should put the safety of the driver, as you said,
yes, the safety
in the first, budget or
yes, the safety is always the first thing to care about.
Okay, thank you.
Bene, abbiamo concluso la fase di presentazione e discussione delle tesi. Vi avevo anticipato, a questo punto la commissione si deve riunire per valutare il lavoro di tesi dei vari candidati. Quindi vi chiediamo gentilmente di accomodarvi fuori dall'aula e come è scritto nella convocazione, orientativamente l'orario delle proclamazioni sarà le 12:45. Bene, allora possiamo procedere con la fase di proclamazione dei candidati, partendo dagli studenti della laurea triennale in ordine alfabetico, e poi passeremo agli studenti della laurea magistrale e poi concluderemo con un breve saluto da parte del Presidente della Commissione, che come vedete è quello vestito di nero. Ok, allora partiamo con la laurea triennale, partiamo con Barbieri Filippo. Barbieri Filippo, la Commissione ha preso atto del curriculum dei suoi studi e dopo aver valutato la sua prova finale ha approvato il suo esame di laurea con il punteggio di 110 e lode. Pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me delegati, la dichiaro e proclamo dottore in ingegneria elettronica. Complimenti. Cavazzuti Tommaso. La Commissione ha preso atto del curriculum dei suoi studi e dopo aver valutato la sua prova finale ha approvato il suo esame di laurea con il punteggio di 98 su 110. Pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me delegati, la dichiaro e proclamo dottore in ingegneria elettronica. Complimenti. Cozza Emanuele. La Commissione ha preso atto del curriculum dei suoi studi e dopo aver valutato la sua prova finale ha approvato il suo esame di laurea con il punteggio di 110 e lode. Pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me delegati, la dichiaro e proclamo dottore in ingegneria elettronica. Gola Gianmarco. La Commissione ha preso atto del curriculum dei suoi studi e dopo aver valutato la sua prova finale ha approvato il suo esame di laurea con il punteggio di 109 su 110. Pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me delegati, la dichiaro e proclamo dottore in ingegneria elettronica. Cafi Atanas. La Commissione ha preso atto del curriculum dei suoi studi e dopo aver valutato il punteggio della sua prova finale ha approvato il suo esame di laurea con il punteggio di 97 su 110. Pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me delegati, la dichiaro e proclamo dottore in ingegneria elettronica. Complimenti. Lambertini Alessandro. La Commissione ha preso atto del curriculum dei suoi studi e dopo aver valutato la sua prova finale ha approvato il suo esame di laurea con il punteggio di 110 e lode. Pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me delegati, la dichiaro e proclamo dottore in ingegneria elettronica. Complimenti. Ronchi Francesco. La Commissione ha preso atto del curriculum dei suoi studi e dopo aver valutato la sua prova finale ha approvato il suo esame di laurea con il punteggio di 104 su 110. Pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me delegati, la dichiaro e proclamo dottore in ingegneria elettronica. Complimenti. Rubaltelli Chiara. La Commissione ha preso atto del curriculum dei suoi studi e dopo aver valutato la sua prova finale ha approvato il suo esame di laurea con il punteggio di 108 su 110. Pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me delegati, la dichiaro e proclamo dottore in ingegneria elettronica. Serafini Luca. La Commissione ha preso atto del curriculum dei suoi studi e dopo aver valutato la sua prova finale ha approvato il suo esame di laurea con il punteggio di 109 su 110. Pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me delegati, la dichiaro e proclamo dottore in ingegneria elettronica. Complimenti. Sissa Giacomo. La Commissione ha preso atto del curriculum dei suoi studi e dopo aver valutato la sua prova finale ha approvato il suo esame di laurea con il punteggio di 90 su 110. Pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me delegati, la dichiaro e proclamo dottore in ingegneria elettronica. Complimenti. Spaggiari Giacomo. La Commissione ha preso atto del curriculum dei suoi studi e dopo aver valutato la sua prova finale ha approvato il suo esame di laurea con il punteggio di 110 e lode. Pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me delegati, la dichiaro e proclamo dottore in ingegneria elettronica. Complimenti. Tebaldi Marco. La Commissione ha preso atto del curriculum dei suoi studi e dopo aver valutato la sua prova finale ha approvato il suo esame di laurea con il punteggio di 106 su 110. Pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me delegati, la dichiaro e proclamo dottore in ingegneria elettronica. Complimenti. Tiri Valerio. La Commissione ha preso atto del curriculum dei suoi studi e dopo aver valutato la sua prova finale ha approvato il suo esame di laurea con il punteggio di 97 su 110. Pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me delegati, la dichiaro e proclamo dottore in ingegneria elettronica. Complimenti. Bene, veniamo ora ai laureati magistrali, ai laureandi, ancora per poco, magistrali. Bergamini Francesco. La Commissione ha preso atto del curriculum dei suoi studi e dopo aver valutato il suo lavoro di tesi ha approvato il suo esame di laurea con il punteggio di 103 su 110. Pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me delegati, la dichiaro e proclamo dottore magistrali in Electronics Engineering. Carboni Giovanni. La Commissione ha preso atto del curriculum dei suoi studi e dopo aver valutato il suo lavoro di tesi ha approvato il suo esame di laurea con il punteggio di 110 e lode. Pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me delegati, la dichiaro e proclamo dottore magistrale in Electronics Engineering. Pratisoli Angelica. La Commissione ha preso atto del curriculum dei suoi studi e dopo aver valutato il suo lavoro di tesi ha approvato il suo esame di laurea con il punteggio di 110 su 110. Pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me delegati, la dichiaro e proclamo dottore magistrale in Electronics Engineering. Soli Elena. La Commissione ha preso atto del curriculum dei suoi studi e dopo aver valutato il suo lavoro di tesi ha approvato il suo esame di laurea con il punteggio di 110 e lode. Pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me delegati, la dichiaro e proclamo dottore magistrale in Electronics Engineering. Sonaglia Daniele. La Commissione ha preso atto del curriculum dei suoi studi e dopo aver valutato il suo lavoro di tesi ha approvato il suo esame di laurea con il punteggio di 110 su 110. Pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me delegati, la dichiaro e proclamo dottore magistrale in Electronics Engineering. Tondelli Elisa. La Commissione ha preso atto del curriculum dei suoi studi e dopo aver valutato il suo lavoro di tesi ha approvato il suo esame di laurea con il punteggio di 110 e lode. Pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me delegati, la dichiaro e proclamo dottore magistrale in Electronics Engineering. Vignoli Elia. La Commissione ha preso atto del curriculum dei suoi studi e dopo aver valutato il suo lavoro di tesi ha approvato il suo esame di laurea con il punteggio di 110 e lode. Pertanto, per i poteri conferiti dalla legge al rettore di questa università e a me delegati, la dichiaro e proclamo dottore magistrale in Electronics Engineering. Bene, penso che adesso i neodottori, i dottori magistrali saranno un po' più sollevati e un po' più rilassati. Non posso non cominciare senza fare complimenti e le congratulazioni ai neodottori magistrali per questo importante risultato raggiunto dopo anni di studio che hanno richiesto sacrifici, perseveranza ma anche entusiasmo. Questo è è un punto di arrivo per voi dopo un percorso appunto che ha richiesto un certo impegno, punto al quale siete arrivati dopo, chiaramente, come dice anche la formula di proclamazione, aver concluso il vostro percorso di studi e dopo aver dimostrato, per quel che riguarda i laureati triennali, attraverso la prova finale, la capacità di applicare le conoscenze acquisite durante il curriculum in modo autonomo e indipendente, e per quel che riguarda i laureati magistrali, quella di svolgere, diciamo così, di affrontare dei cosiddetti problemi aperti, cioè problemi che al momento non prevedono ancora soluzioni o che le cui soluzioni sono appena state presentate e quindi necessitano delle giuste valutazioni, delle giuste analisi, svolte o all'interno dei laboratori di ricerca del nostro dipartimento o all'interno delle sezioni di ricerca e sviluppo delle aziende presso le quali hanno svolto la loro attività. Per quel che riguarda i laureati magistrali, insomma, mi fa anche piacere che non è la prima volta che mi capita sottolineare il fatto che abbiamo una quasi parità o una parità di genere. È una cosa che ci fa piacere, perché significa che comunque l'ingegneria elettronica inizia a suscitare anche un certo interesse nei confronto del genere femminile. Abbiamo ancora molta strada da percorrere da questo punto di vista, però insomma i segnali sono per noi incoraggianti. Come dicevo, per quel che riguarda la laurea magistrale, sono attività che hanno richiesto un contributo originale da parte degli studenti, svolti all'interno dei laboratori di ricerca o di ricerca e sviluppo delle aziende. Ci tengo a dire questo perché non sempre è percepito da chi non vive, diciamo così, dall'interno dell'università, che il cuore pulsante di un'università è l'attività di ricerca. È dall'attività di ricerca poi che si trae la linfa vitale che va ad arricchire l'attività didattica che i vari docenti fanno nella laurea triennale e nella laurea magistrale, perché solo facendo attività di ricerca che un docente mantiene l'aggiornamento necessario per garantire una didattica di qualità, ed è anche linfa feconda per le collaborazioni che i vari docenti all'interno del dipartimento hanno con le varie aziende con le quali magari collaborano proprio per cercare, a fronte del bagaglio di conoscenze accumulate durante l'attività di ricerca, di risolvere problemi che in quel momento, come dicevo prima, sono problemi aperti, cioè non hanno ancora una soluzione definita. Come tutti i punti di arrivo, un punto di arrivo è anche un punto di partenza, nel senso che adesso, a seconda delle vostre aspirazioni, delle vostre scelte, c'è chi deciderà di andare, diciamo così, immergersi nel mondo del lavoro, e questo non dovrebbe essere un particolare problema per un ingegnere, ancor meno per un ingegnere elettronico, visto che, diciamo così, la richiesta di ingegneri elettronici è largamente superiore a quello che è il numero di studenti che periodicamente si laureano. Questo sta creando anche dei problemi abbastanza seri da parte delle aziende, che appunto fanno fatica ad trovare personale adeguatamente qualificato. Altri di voi della laurea triennale decideranno di proseguire gli studi e continuare con una laurea magistrale, o all'interno del nostro dipartimento, del nostro ateneo, o presso altri dipartimenti, presso altri atenei. In questo caso comunque presentandovi di fronte alla nuova sfida con un bagaglio di conoscenze e di competenze più che adeguato appunto per affrontare il nuovo percorso. Alcuni laureati magistrali poi decideranno di proseguire i loro studi, magari all'interno di un dottorato di ricerca, che, come vi ricordo, è è il titolo di studio più elevato riconosciuto non solo dall'ordinamento italiano, ma dall'ordinamento europeo e diciamo forse di quasi tutti i paesi avanzati. Quindi quello che sia la vostra scelta e quello che sia la vostra nuova tappa, quello che mi sento di dire a nome mio, di tutta la Commissione e di tutti i docenti che in un qualche modo avete incontrato durante il vostro percorso qui all'interno del Dipartimento di Ingegneria Enzo Ferrari, è un grandissimo in bocca al lupo per il futuro. Grazie. Va bene, adesso sono aperti i festeggiamenti, come ha detto il direttore, al di fuori del perimetro del Dipartimento.